The Jacobi method is what we call an iterative method for solving a system of equations. The way it works is we will start out with a guess for the unknowns x1, x2, and x3, and we'll insert that guess into a system of three equations to obtain a new result for each of those, x1, x2, and x3. That new result is then put into the same system again to get another new result, and so on, with the hopes that the values we get each time for x1 and x2 and x3 are approaching a solution to the system of equations. So the first thing we do to execute the Jacobi method is we need to take our system and we solve the first equation for x1, the second one for x2, and the third one for x3. So let's do that for the first one. You can see that we'll subtract, or we'll take, we'll have 12 plus x2 minus 2x3. And then we have to divide that by 5. And that will give us our value for x1. So we can do the same thing to get equations for x2 and x3. Once we have those three equations, then what we do is we take our initial guess. We'll have an initial guess for x1, x2, and x3. You can see we put just our initial x2 and x3 into the first equation to get a new x1. We put our initial x1 and x3 into the second one to get a second value for x2. And we put the initial x1 and x2 into the third equation to get our next value for x3. So let's start off by drawing ourselves a table in which we'll keep track of the values. So let me do that. So here's the table I've come up with. Ordinarily in mathematics, we would call our starting values, we would actually index those with a 0. But I'm going to use a 1 here because we want to think in terms of perhaps programming this into MATLAB eventually. And so MATLAB generally won't let us have a sequence with an index starting at 0. So let's start our index at 1. So let's suppose that we take an initial guess of 0 for each of x1 and x2 and x3. And let's see how we go on and get our next values. So our next x1 we obtain using the first equation up here to the right. So our next x1 will be 12 plus our x2 from the first time around, which is 0, so plus 0, minus 2 times our x3, which is also 0, over 5. Okay, so what we get out of that is we get 12/5, which in decimal is 2.4. Okay, so that's our next x1. We do a similar process to find the next x2. So the next x2 is going to be negative 25 minus 0, because our x1 and x3 are currently 0, over 8. So that's negative 4.025, excuse me, that's negative 3.125. And similarly, we do the same kind of process, and we get that our next x3 is going to be 6 over 4, or 1.5. Okay, and so now we have our new values. Let me just box those. So here's our new x1, 2.4. Our new x2 is negative 3.125. And our new x3 is 1.5. So let's go on and let's do one more iteration. So we'll find our values for the third time around. Again, the first time just being our initial guesses. So now I have x1 equals 12, and then it's plus x2. So this is going to be plus negative 3.125. And then it's minus 2x3, so minus 2 times 1.5. And that's all divided by 5. And I did that ahead of time. That value comes out to be 0.815. our x2 the next time around, we take negative 25 minus 3 times our previous x1, which is 2.4, plus 2 times our previous x3, which is 1.5. And that all is divided by 8. And when we do that, we get negative 3.65. And finally, to get our next x3, we use the equation 6 minus our previous x1, so that's 2.4, minus our previous x2, so that's minus negative 3.125, all over 4. And so the result here is 1.68125. Now, it turns out that the actual values of these things are that x1 is 1, x2 is negative 3, and x3 is 2. That's the actual solution to the system of equations. So you can see that we're still not quite there. Instead of 1, we have 0.815. Instead of 3, we have negative 3.65. And instead of 2, we have 1.68125. But within a couple more iterations, we would most likely be getting pretty close to that exact solution. So that's how the Jacobi method works. In the next video, we'll take a look at the Gauss-Seidel method, which is quite similar.